All right, continuing on, we've got to determine the roots of a polynomial. And the way we're going to do that is by doing something called the rational root theorem. And what the rational root theorem says is that if you take the last number of your polynomial and you find all of its factors, and you take the first value of your polynomial and you write down all of its factors, then any p divided by any q is a possible solution or a possible root to this polynomial. Now, there could be imaginary roots that won't necessarily show up in this list, but any real root will either be 1, 2, 3, 5, 6, 10, 15, or 30, or 1 half, that's 1, 3 halves, 5 halves, 3, 5, 15 over 2 and 30 over 2, which is 15. So if you notice, some of these, when you divide them, become roots you already had in the list anyways, so you don't really have to consider them as another solution. You've already kind of considered those. So how are we going to do this? We're going to do this using synthetic division. And I've not done this ahead of time. Maybe I should have. But I'm just going to try from the beginning. I'll try positive 1. Let's see if 1 is a root. Bring down 2. We bring the first value down and multiply. That answer gets written right here. We combine these. In this case, it'll be addition. It's kind of addition always, but that'll be 9. Now I multiply again. I get 9. Now I combine through addition, which since I have a negative and I'm adding 9, I'm really subtracting. That's going to be negative 17. Multiply. And I can kind of already tell where this is going. It does not look like this is going to end up being 0 at the end. So 1 is evidently not a root. Well, what do? We erase it all and restart. And it's a fire drill. How exciting. Cool. And now we try negative 1. So we get negative 2. It's 5. This is fun. We get negative, what would that be, 31. Now we get 31. Again, it looks like I'm not getting 0. So evidently 1 or negative 1 are not roots. This could end up being a little time consuming here. The goal is to not use a calculator to do these, though. Let's try 2. Bring down 2, multiply, that's 4. It's 11, that's 22. Negative 4, negative 8. Again, I can already tell that's not going to end up being 0 in the end. Let's try negative 2. It's negative 4, 3, negative 6. That would be negative 32. Positive 64. Oh, we're finally getting somewhere. That's 15, which means now I get negative 30, which I finally get 0. Yay, so I found my first root. My first root is negative 2. Now, one thing to consider is now your rational roots should only be based on these numbers. This is the first term of the polynomial. It's now 2x cubed, and the last number, instead of being plus 30, will be plus 15, if you kind of remember how you rewrite this. So now I definitely know that, negative 2 is not a root again, because 2 doesn't divide into 15. So I should be trying 3, 5, or 3 halves, or 5 halves. So let's try 3. Or their negatives. It's going to be 6, 9, 27, negative 5, and look at that, negative 15. I found my second root. Now at this point, this is a quadratic. And what I said before is I think truly the quickest way to get through a quadratic in this case would be just factoring by grouping. I'll find my last 2 roots. Again, this is nice. There's only one way to make 2x squared. There's 2x and x. There's also only one way to make 5. It's 1 and 5. So where do the 1s and 5s goes? I can kind of already see they're going to go here because I make 10 and 1. And yes, I can subtract 10 and 1 to make 9. So the plus goes here, the minus goes here. That gives me positive 10 and negative 1 to give me positive 9 in the middle. That multiplies to negative 5. This is so fun. And so together, all my roots are negative 2, 3, 1 half, and negative 5. Now, what are roots in general? Well, roots are ways of understanding what this polynomial looks like when it's graphed. So if I want to graph this polynomial, I'll graph a root at negative 5, a root at negative 2 on the x-axis, a root at 1 half, and a root at 3. I'm just kind of guesstimating those placements. But since this is a positive even polynomial, any positive even ends by going up and to the left and up and to the right. And since these are all single roots, they will pass through the x-axis. So I get a polynomial that is in general shaped something like that. So that's the whole point of finding roots, so that you can understand where your graph is going from the positive side of the x-axis to the negative side of the x. I guess actually positive side of the y-axis to the negative side of the y-axis by crossing through the x-axis. That is what roots tell you. Where is this polynomial, or rather, what value can you substitute into this polynomial to make the whole polynomial equal 0? That's why they sometimes call them roots, zeros, or intercepts. Roots, zeros, where is the y value 0, or intercepts, where am I crossing the x-axis? What a long time to find roots. All right, now we're going to do the opposite of what we just did. So we just had a giant polynomial, and we deconstructed it to its roots. Now we're going to take the roots and construct the polynomial. So when I go from roots to algebra, the signs switch. Now the reason for that is because what I said before, we're trying to find what makes my polynomial or quadratic equal 0. Well, if negative 7 makes my quadratic equal 0, then plugging in negative 7 has to make this root equal 0. So negative 7 plus 7 is 0. So that's why the sign kind of switches in a sense, because you're making this parentheses equal 0 when negative 7 is plugged in. Now I want to FOIL that out. I'm going to do that in my head. I'm going to get x squared. I'm going to get negative 3x and positive 7x, which will be 4x, and then negative 21. So I'm done. Up next, I've got a polynomial with a few more roots. That'll be x minus 3, x plus 4, x minus 2, x plus 2. Now, in this case, this is a difference of squares, but it's polynomial. Well, I just realized I did that totally wrong because I wrote my initial values wrong. Here we go. Those are my roots in order. I wrote x plus 4. Sorry about that. So, again, same idea. I'm going to FOIL out these two first. They're a difference of squares. That'll make my FOILing easy. It's going to be x squared minus 4. You can check that. When I FOIL these two out next, that'd be my move. I don't want to FOIL out this term to the difference of squares and then this term to the difference of squares. To me, that seems like more work. I can FOIL this out faster. I'm going to get that as my answer. And now I have to FOIL these two out together, so I'll do that with a little bit more work here. I'm going to get an x to the 4th. Okay. Then I'm going to get a negative 4x squared. And notice I'm already leaving some intentional space just in case an x cubed term comes along. Why not go in order? Here is my x cubed term, negative 7x cubed. And then I'm going to get positive 28x. Last but not least, I'll get 12x squared. Notice I'm going to write that underneath the other x squared term, so my like terms are easier to combine. I can see them more closely together. I don't miss one. Rather than having a giant line and crossing them out as I go, try to anticipate what your answer is going to look like to save yourself some of that work. And we're going to get x to the 4th minus 7x cubed plus 8x squared plus 28x minus 48 after I checked Wolfram Alpha because that's a lot of FOILing and room for mistakes. Let's see, am I right? Yay. All right, we did it. Now we're moving into our graphing section. So first we've got a quadratic 2 graph, and this is just in standard form. Now what I'm going to do is two things. First, I'm going to see if I can factor this. Factors of 12 that subtract to 4 are 6 and 2. So now I know what the roots are. The roots are at 2, and the roots are at negative 6. Now what I could also do here is I could figure out where the vertex is. The coordinate of the vertex is going to be negative b over 2a, which will be negative 2. So now I know the vertex is, let's see here. Yep. Is that right? Something doesn't feel right here. Because that's not negative 6, that's negative 5. Negative 2. There we go. I know the vertex is down here. Now it's probably going to be really, really far below. Let's see what happens when I plug in negative 2. The y-coordinate is going to be 4 minus 8, which is negative 4. So the y-coordinate would be negative 16. So the vertex is negative 2, negative 16. So yeah, a little bit too low to see, but quadratic has some sort of shape like that, where that is negative 2, negative 16. All right, now why did I know the graph was off there? Why did I know one of those was spaced incorrectly? Well, because the vertex is always is going to have some symmetry, or rather there is an axis of symmetry that goes through the vertex in a quadratic. So the amount of space to this root should be 4 away from the vertex and 4 away, in this case 4 away. But your vertex is always going to be directly in between your two roots in a quadratic. So that's why I knew where it would be, and I knew this was 1 off when I looked at that really quickly. Up next, this is in vertex form, so this actually makes our life way easier. The vertex is going to be the point 2, 4. All right, so right 2, up 4, and this is a standard quadratic. Now I'm going to be a little more detailed here. This is a equals 1 quadratic, which means when you move right 1, you'll go up 1, left 1, you'll go up 1, because you're squaring moving left or right, so it becomes positive motion. When you move right 2, you'll go up 4, because quadratics square things. So that's how the quadratic gets its shape. If you move right 2, you go up 4. If you move left 2, you go up 4, because again, positive 2 or negative 2, once it's squared, becomes positive 4. You're moving up 4 for any right 2 or left 2 movement. So if you go right 3 or left 3, you'll be going up 9 and 9. That's how we get our shapes. Again, that's also how I knew that this vertex was going to be very, very far away, because I know if I moved it 4 and 4 away when A is 1, I knew my vertex was going to be 16 units down in my head. I just didn't want to lead into that right off the bat. Okay, up next we've got a square root function in vertex form. Now that vertex is right 3, down 2, and it's vertically stretched by 2. Now a square root is the inverse of a square function. So usually this would go right 1 up 1, or right 4 up 2, or right 9 up 3, but now we're doubling that vertical movement. So I'll go right 1 up 2, I'll go right 4 up 4,